Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki, and I'm a theoretical physicist who specializes in cosmology. That means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the cool things happening inside the universe. I love being a scientist, I love being a cosmologist, and I'm always really happy to chat to everyone about all of the cool stuff happening in the universe. So I'm live on YouTube and on Twitter on Cup of Cosmology to talk to everyone about space, about science, about cosmology. And as always, this is an Ask Me Anything. This is an interactive stream, so you can ask me anything you want, preferably on topic, but you're also always welcome to go off topic as well. Anything you want to know about cosmology, about science, about basically everything that I work on, or academia in general, you are always welcome to ask. Obviously, I won't have all the answers, but I will do my best to answer any questions you all have. And just going to say hello to all of the people tuning in here. A lot of the regulars. Hey, Anne, Scott, David Dunn, and David Howden. Great to see you all. Thank you for being here. As always, my core followers, you're always here every week in and out. It's always great to see you all here as well. So thank you for tuning in. To anybody new who's watching, welcome. I hope you stay. I hope you enjoy what you're hearing here. To the regulars, as always, welcome back. It is great to see you here every week. If you do like this stream, if you like what you're hearing here, please do subscribe to the YouTube channel, leave a comment, click the like button, all of the usual things to boost visibility for the channel. I'm still building up my audience after having to move platform again a month ago. So any engagement you give to the video really does help spread it out there and make the channel grow. So thank you for any reactions, any comments, anything. And if you want to support Cup of Cosmology, there is a link down below in the YouTube stream where you can go to my Buy Me a Coffee page if you feel like supporting me. Of course, absolutely no pressure or obligation there, but I appreciate any and all support from all of you. And hey, Paul, great to see you as well. And thank you for the congratulations. So yeah, I'm pretty excited this week. I put a new paper online. So please like the broadcast, exactly like, subscribe, all the usual stuff. So the academic publishing process has several different parts. Usually what happens, especially in my field, is we finish writing a paper and we put it on the archive. Now the archive is open access. This is the first place where we put our our new results, our new papers. This does not yet mean it has been published in a journal. This is just the first step. So we put it on the archive, we get some feedback from the community, we get people saying you forgot to cite me, which is always going to happen, we always forget things. Then we submit the paper to a journal, it gets refereed by some peers, some of our peers look at the paper, it goes through a bit of back and forth between the referees and the authors, and then hopefully it gets accepted in a journal. So the paper is now on the archive. This means that it is not yet peer reviewed and it is not yet in a journal, but we have now put it out there. We think that the paper is ready to be out there in the world. This is a paper we put on the archive this week. Again, the link should be down below in the YouTube comments, in the video description. There should be a link to the paper. If you already want to click on that, you are welcome to do so. And I'm super, super excited about this because this is a project that I started back during my PhD. So back in 2018, March 2018, we started on this project. That means it's been over 4 years and 3 months since we started this paper. And it has seen so many issues. There have been so many setbacks and numerical issues. There have been days where we didn't think we would ever finish this paper. There have been days where we didn't think what we were doing was possible, where we didn't think the results would be worth publishing. And, this is probably the paper I've been involved in that's had the most setbacks and that has taken us the longest. But now, after over 4 years, we're satisfied, we're happy with what we've done. We've done everything we set out to do and more. And I'm really excited to tell you all about this paper. So let me just start by, let's see if I can do this properly. This should be the way it works. And let me just take that one off. Still getting used to the new setup, so it takes me a while to press all the right buttons. So thank you to everyone sending the congratulations messages. I do appreciate it. So this is my new paper. This is how it appeared on the archive on Friday morning. We put it on the archive on Thursday, so it appeared on Friday morning. So my new paper has the very fun title, One Likelihood to Bind Them All, Lyman-alpha Constraints on Non-Standard Dark Matter. And as you can see here from the author list, there are 6 authors involved in this paper, and I was the lead author on this project. And it's finally done. It's a 35-page paper, and it's out there in the world now. So One Likelihood to Bind Them All, Lyman-alpha Constraints on Non-Standard Dark Matter. And just want to make a comment here that I am highly amused by the title of the paper, because it's always fun to try to come up with titles that are both funny and creative and actually descriptive for the paper. And this is probably my second favorite paper title that I come up with. So I'm closely behind the one where I managed to come up with a cannibalism pun in the title of my paper. The paper was on cannibal dark matter, so the cannibalism pun was very justified. Okay, so thank you for the comment that you love the name. Honestly, I do too. That was a random moment of like, oh, I just came up with this title and put it there, and all my co-authors agreed with it. So that's the title we're going with. So I'm going to talk to you today about the paper. As always, you can ask me any questions you want, regardless of your level, regardless of your background. You can ask me anything. As always, there are no stupid questions. There are just unasked questions. So whatever you want to ask, you feel free. There is absolutely no stupid questions out there. Prepared for submission to JCAP, does that mean they still haven't accepted it for publication? Exactly. So we haven't even submitted it to JCAP yet. So JCAP is the journal we are submitting to. It's a journal for cosmology and astroparticle physics. It's the one I usually submit my papers to. And this, what we mean here is we put it online, we've put it on the archive, and next week, once we've got a bit of feedback from the community, next week we will submit it to JCAP, and then we wait for feedback from JCAP. The link in the description does not work because the right parenthesis included in the link. Okay. So thank you for pointing that out. I can't change it live. I think, no, I can't change this while I'm live, but then you can just correct the link, remove the last parenthesis, and I will correct it in the YouTube description afterwards. Thank you for telling me that, David. Still figuring out how Restream works and how it does and doesn't send the links. So that is good to know. That is very good to know. You have a quick question unrelated to this? Go ahead, Scott, as always. Is there a cosmic string formed into a ring in it? So we don't do cosmic strings in this paper just yet. I am working on cosmic strings for other ones, but no cosmic strings in this paper just yet. How do you know your co-authors? That is a great question, David, actually. So this is a project that I started during my PhD in Aachen. Now, when at the time, all 6 of the co-authors were in Aachen. So myself, I was a PhD student in Aachen. Niels Schoenberg was a PhD student in Aachen. He's now a postdoc in Barcelona. Riccardo Muggia is now an assistant professor in L'Aquila in Italy. He was visiting us as a student. Then Maria Ciliacona was a postdoc in Aachen at the time when we started. Julian Lesgo is my PhD advisor, professor in Aachen, and Matteo Fiel was not in Aachen, but he was Riccardo Muggia's PhD advisor and a close friend of all of us. So that's how we all got to know each other. But this was a project that was started in Aachen when we were, at least 5 of us were there. Then we scattered, but the project continued. But it's curious, some of my co-authors I've never met in person. I have people that I've published papers with who I've never met in person. So that's always fun. I remember reading that one of Einstein's relativity papers languished for some time before being appreciated. That does happen sometimes, that sometimes you put a paper out and it requires a bit of time before the community notices, or sometimes there's issues, and sometimes people might not realize the importance of a paper until someone else does the next step. So that is always the issue. I saw a video suggested here on YouTube with a clickbaity title alleging that JWST was struck by a meteorite. That is actually true. There was a very small space rock that hit the JWST telescope very recently. JWST, that's a tautology. The JWST was hit by a very small asteroid very recently. It was slightly bigger than they expected, but it's also something that can happen, and it did not damage a spacecraft in any way. It did not damage the telescope in any way. But, maybe, I guess, if you name your telescope after a homophobe, space is going to throw rocks at it. But anyway, yes, that did happen. It was hit by an asteroid. by a tiny, not an asteroid, sorry, by a tiny chunk of rock, tiny meteor. That did happen. And I believe David Dunn did do a video about this over on Twitch on the astronomy show, so do check that out as well. David Dunn is our, I say local astronomy professor, does the astronomy professor who live streams. Do check that out as well. So I want to tell you a bit about this paper, why we did it, what we were hoping to achieve, and what we found. Because apart from all of the work that's gone into this, we have found a couple of cool things, actually. They're things that I think are worth talking about and worth mentioning. 0.1 millimeter particle, so a very tiny space rock. But even tiny space rocks traveling at enough speed can do a lot of damage because there's no air friction to slow them down. So they can travel at a bit of speed, they can do a bit of damage. Okay, so before we get started, I want to look at this title. The title of my paper, I mentioned Lyman-alpha, I mentioned a likelihood, and I mentioned non-standard dark matter. So before jumping into what we actually did in the paper, I just want to make sure we're all on the same page about what these three things are. Now, the first one, we're going to start with dark matter. You read your paper, and I'm amazed at the amount of work. Thank you, Shri. Currently a master's student working towards a PhD in cosmology. Awesome. I'm so glad to see other physicists tuning into these streams as well. And I'm wondering if you heard of this stream from the Discord server. If so, awesome. If not, from wherever you heard about this stream from, it's awesome to have a fellow physicist here in the room as well. So, non-standard dark matter. Let's explore the forest. We're going to get to the forest as well. I know Lyman-alpha forest is in the title of the stream. We're going to get to that. First of all, what do I mean by non-standard dark matter? Now, everything we know of in the universe, everything we can see, everything from me to the sky, to the stars we see in the night sky, to my tea mug, all of this is normal matter. Now, normal matter only accounts for 5% of the energy budget of the observable universe. Then there's another 25% that is in the form of dark matter. Now, dark matter is a strange type of matter that doesn't interact with anything else except via the gravitational force. It does not emit light, it does not absorb light. As far as light is concerned, it's invisible, but it does interact gravitationally. And then there's this other remaining 70% of the energy budget of the observable universe, which is in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. But dark matter. Within our standard model of cosmology, the best model we have to explain the universe so far, this model is known as lambda CDM, and the CDM part here stands for cold dark matter. Now, what we mean by cold in this case is that the dark matter doesn't really bump into other things, it doesn't interact, and it's traveling relatively slowly. If you change either of these two assumptions, if you make your dark matter travel a bit quicker, or if you make your dark matter have interactions, it no longer falls under the standard cold dark matter paradigm that we consider. And there's a lot of different words you can use once you move away from the cold dark matter paradigm. Depending on how you're moving away, you prefer to interacting dark matter or to non-cold dark matter. Now here, because we look at multiple different types of dark matter that are all beyond the standard cold dark matter, we opted for the name non-standard dark matter. So what we mean by non-standard dark matter is dark matter that has either more interactions or that has slightly larger velocities or speeds than what we expected. Are there Ents in the Lyman-alpha forest? Probably not, but I do appreciate the Lord of the Rings references. You Googled your name on the internet because of the paper. Oh, thank you. That is awesome. That is really nice that from my paper you found the live stream. I love that. That is really, really cool. Thank you for joining here, and thank you for being here. The dark matter in your friend's game traveled pretty fast. Yeah, we developed a smartphone game called Dark Master where you can play about with dark matter. Yeah, it does travel annoyingly fast, but in general, dark matter is relatively slow and doesn't interact. Now, in this paper, we're looking at dark matter that does either of those things, and we call this non-standard dark matter. Next up, in the title, we have the word likelihood. Now, I just wanted to say I'm not going to go into a lot of details as to what a likelihood is, but a likelihood is basically something that lets you go from data to model. So often you might have a lot of different models in cosmology or in physics or in general, and a lot of these different models make different predictions. And what you do here is you take your model with its prediction, and you want to see how accurate this prediction is based on the data that we have available. And this link that allows you to go from the data to the model and vice versa is what we call a likelihood. When you say dark matter interactions, are you referring to gravitational effects detected? No, when I say dark matter interactions here, I mean beyond gravitational. So for an example, maybe dark matter could have a tiny interaction with standard model particles. Maybe they can bump off to each other. Maybe they can exchange some type of boson. We don't know what boson. So when I'm talking about dark matter interactions here, I mean not gravitational interactions, but other interactions. Now, the standard picture of dark matter is that dark matter does not have these other interactions, which is why we say it is non-standard dark matter. So, likelihood lets us connect data and model, and non-standard dark matter we've covered, and the last piece is Lyman-alpha data. So, let's get into what Lyman-alpha data is, and then we'll bring it back to the paper. So, Lyman-alpha data, or the Lyman-alpha forest. Now, when you look at the light coming from a distant quasar, this light has to travel towards us. So a quasar is just a very, very bright galaxy that's far away that you can see very brightly in the night sky. Now, as this light travels towards us, it is going to travel through the intergalactic medium. Now, intergalactic medium is just the space in between galaxies. The space in between galaxies is largely empty, but it does have some very small clumps of hydrogen clouds. As the light from this distant quasar is going to travel towards us, it's going to pass through these hydrogen clouds. Now, at this point, it's going to trigger a series of absorption and emission lines. The photons are going to be absorbed by an electron and re-emitted, absorbed and re-emitted. And this leads to a series of what we call absorption and emission lines. And these absorption and emission lines, I'm going to bring up an image as soon as I can find the image I want to bring up, because I thought I had it ready, but apparently I do not. And of course, it's the last one that I'm going to find. So these series of absorption and emission lines actually tell us a lot about the hydrogen clouds in the intergalactic medium. So just to show you what I mean here, I'm going to bring up this image. Now, what you can see here, focus on the top panel first of all. You have this background quasar kind of in the center of the screen. This background quasar is traveling to the Earth, towards us. In between this, there is some intervening gas. There is some hydrogen gas. By the time the light from this quasar reaches us and we take its spectrum, which means we just decompose its light, what we're going to see is this series of absorption and emission lines. So basically, if you hold up a prism, you might all know that a prism basically creates a rainbow. You have incoming light, you shine a prism to it, you get a rainbow coming out. It decomposes the light into its wavelengths. Now, if you do this to the light coming from a distant quasar, you will get this prism spectral decomposition, but there will be a series of black lines on it. And the black lines correspond to places where there was an absorption or an emission in the hydrogen cloud. Hey, Abyss, great to see you. It's always nice to have you in the room, Abyss. So what you can see here on screen is a cartoon image of what happens when the light from a distant quasar travels towards us. And you can see there's this mess of black lines, which we refer to here as the hydrogen absorption. Now, these messy black lines are what we call the Lyman-alpha forest. So the Lyman-alpha forest is a series of absorption and emission lines you get when you decompose the light coming from a distant quasar. As always, if there are any questions, if I'm getting too technical, please do let me know. Lyman-alpha data is something I've explained in a lot of talks to my colleagues and to my peers, but it's actually something I haven't explained much on a live stream. So I need to make sure I don't get too technical here, because sometimes it's very easy for me to get lost in the details. I did do a whole live stream at some point about Lyman-alpha data. I will link to it once I figured out how to link in YouTube videos. I will link to it. But the idea is you have this light coming from a distant quasar. This is going to travel through the hydrogen cloud. And by the time it reaches us, you have this messy absorption and emission lines, which we call the Lyman-alpha forest. How do you decompose light? The classic example is to hold a prism up to it, and you get it spread out into multiple different colors. What I mean by decompose light is really just split its wavelength so you can see the different wavelengths that make up the light. The most common example of this that we're all used to is a rainbow. Now, when you're looking at a rainbow, what you're actually seeing is the light from the sun is hitting the raindrops in the sky at a specific angle. And these raindrops act as a prism and break. They spread out the light. So instead of having concentrated white light, what you actually get to see is the wavelength. Now, we can only see a very limited amount of the electromagnetic spectrum from red on one side, ultraviolet on the other. And in that regime, we get this rainbow effect. So when I say decomposed light, what I mean is we're holding up something like a prism or a raindrop that is allowing us to see these different wavelengths. The black absorption bars are very large vertically. Does that mean it is a range of amount of absorption rather than a specific amount? So this really here is just kind of cartoonish image to show you how messy it can get. But if you actually want to see what we really observe when we're looking at Lyman-alpha data, what we actually observe is closer to this here. So this is basically the same as what I was showing before, but an actual real data from a specific thing that we have seen, and not just the cartoon image. So you see on the vertical axis, we have the flux. This is the amount of light coming through. And then we have this series of absorption and emission lines. So this is what we actually observe. So there are these messy black lines everywhere, but this is just to get an idea that you can have absorption and emission lines. I hope that answers the question. Does holding a prism up to sunlight spread out in both directions past UV and infrared? Yes, it should spread out into many more directions than we can actually see, because we can only see light in a specific range. Okay, so Lyman-alpha data is this messy absorption and emission lines. Now, why do we care about this? The reason we care is because if we can understand these absorption and emission lines, we can get an idea of what the hydrogen cloud that caused these lines is actually doing, what it behaves like, and what it, how much hydrogen is there. Now, the reason we care about random hydrogen clouds in the universe is because we know that dark matter in the universe has a strong gravitational force. And in the early universe, dark matter is setting the scaffolding for everything else to fall onto it. This means that where you find a hydrogen cloud, you will find dark matter. The hydrogen cloud fell onto the dark matter due to the gravitational force. So if you can map the hydrogen clouds, you can map what dark matter is doing in these tiny, tiny, tiny regions in between galaxies. This is extremely important. I'm going to show you another image. I've actually made a slideshow, because apparently it's easier to share slideshows than it is to share individual images on Restream. So I now have a slideshow with all of my images, which is nice in principle, but it means every time I want to find an image, I need to go through all 30 of my different pages of the slideshow to find the image that I want to show you, because I didn't put them in the order in which I needed them today. I put them kind of randomly. Okay. So this is an image you've probably all seen before. This is the Millennium simulation. This is a simulation of how matter should be distributed in the universe. And it follows this underlying structure that we call the cosmic web. Now, every glowing dot here corresponds to a galaxy, and you can see that it really does come together in this cosmic web, which is set by the underlying dark matter. So when I'm talking about looking at these really, really tiny clumps of dark matter in between galaxies, if you look at the darker regions here where it looks like there's not much, that's where we can actually think about these hydrogen clouds. So this is interesting because it is some of the smallest behavior we can look at for dark matter. So if we want to know what dark matter does on big scales, we take a bunch of galaxies. But now we want to know what dark matter does on really, really small chunks of the night sky. And to do this, we can use Lyman-alpha data. So Lyman-alpha data allows us to get an idea as to how light is traveling through these hydrogen clouds. These hydrogen clouds allow us to understand what dark matter is doing on these tiny, tiny chunks of night sky. So Lyman-alpha data allows us to understand dark matter. Back to the paper, now that I've gone through a few things. One likelihood to bind them all with a Lord of the Rings reference, Lyman-alpha constraints on non-standard dark matter. So bringing it together now, we have basically developed a method, a likelihood, to go between the data and the model. And in this case, our data is the Lyman-alpha forest, and our models are non-standard dark matter. Okay, I hope that now that we've clarified the title, we can jump into the paper a bit more. Let me just say that one more time here. The point of this paper was to develop a technique, a new method, a new approach to use Lyman-alpha data to understand dark matter. So why do we need a new approach? From what I just told you, this should be pretty straightforward. But there is one step of this process that is very, very difficult. Is one of your favorite images, Sri? Yeah, it's a nice image. It's one of my favorites as well, actually. Now, there's a problem in this step. The step between going from the Lyman-alpha forest, or the amount of light you're receiving, going from that to the underlying dark matter is very, very difficult. Can a dipole oscillation from scattering events be observed when decomposing the spectrum? That is a very interesting question, and off the top of my head, I'm not sure the answer to that. Dipole oscillation. I would have to think about that a bit. As always, you have the questions that stump me, but I will have to think about that and come back to you on that. 25 minutes in, and we've not yet got to Deanna's favorite image. However, the image is in my logo, so technically you have already seen the CMB, because let me just bring this up again, especially now. If you look in the top left corner of your screen, there's my logo, and I've put this on every single image I'm showing now, which means anytime I bring up an image, there is a hidden CMB in it. So actually, you've already seen the CMB a few times today. Haha. I found a way to put the CMB on every single image without it being in your face. It's just my logo hidden up there, nice and discreet in the top left corner. I'm very proud of myself. That's what I spent my time doing this afternoon. Anyway, the step of going from the hydrogen cloud, or from how the light is traveling through this hydrogen cloud, to the underlying amount of matter we have in the universe is very, very difficult. Now, the reason it's difficult is because it's what we call non-linear. Now, by non-linear, we mean that the equations get very complicated. It can't be described by linear equations. We have to go to higher order, more complicated equations. Now, this is a problem because doing things that are linear is easy, it's simple. We like linear things. Going beyond anything that is mathematically linear gets difficult. Now, the problem here is that the way light passes through this hydrogen cloud depends on how the hydrogen cloud behaves. And this requires a simulation. And these simulations depend on all of your underlying model knowledge. So if you change the amount of dark matter you have in the universe, and then you run a simulation to see what the Lyman-alpha flux would look like, you're going to get a different answer. If you make these hydrogen clouds slightly hotter or slightly colder, you're going to get a different answer. Anything you change from your underlying parameters, your model, will have a dramatic impact on the outcome. On this step, every step of the way, you're going to need to run one of these simulations. A comment from Abyss, my rationale is that light emitted as a result of elastic scattering should be noticeable as a bump. So Abyss, I will get back to you on that because I could go, I think it would just take me very much off topic now and I would have to think about the answer. I will try to reply to you in the coming days on that. Okay, so I should also get a drink because I'm just rambling and forgetting about my tea here. I should not forget about my tea because then it gets cold and this tea tastes weird when it gets cold. Okay, so in fact, I want to show you another image here. I'm just going back to the end of my slideshow again because I did not plan the ordering of my slides in an efficient manner today. So let me go back to this one here, or not back to, but let me go back to this one here. Now, this is what I already showed you, this mock idea of the Lyman-alpha forest. But what we actually observe, what we're actually interested in, is what we call the Lyman-alpha flux. So what you can see here on the vertical axis is the flux, so the amount of light that is coming from these distant quasars, not so much the amount of light that is coming from the quasar itself, but how much of this light reaches you. Okay, now your questions are always welcome. I will come back to your question. Just probably not today, but I will come back to it. So we have the flux, and on the horizontal axis, we basically have a velocity, but we can use this to get an idea as to the scales we're looking at, the sizes we're looking at. Is that the cucumber tea again? Yes, it is. This is indeed cucumber and strawberry green tea. It has green tea in it, strawberries and cucumber. And it is weird, but also somehow I like it until it gets cold. When it gets cold, it is not good. Okay, that is a great question from Sri. I will get to you in one sec about why hydrogen clouds. But first, let me just finish going through this figure here. So on the horizontal axis, we're getting an idea as to how small we're looking in the night sky. And on the vertical axis, the amount of light that we're getting from these hydrogen clouds. Now, every point, every dot that you can see here corresponds to data that we actually have. In the bottom left, we have data from the Sloan Digital Sky Survey. And in the top right, we have data from MIC and HIRES. So MIC data and HIRES data are shown with the triangles and the rhombus being MIC, the triangles being HIRES, and then everything else is SDSS data in the bottom left. And what you can see is that there are these kind of horizontal bands. Now, these horizontal bands correspond to a specific distance of the quasars that you're looking at. Now, we take all of the quasars we have, and then we plot them on different redshift bins. So this is the actual data we get from Lyman-alpha data. But to go from this here, from this flux, to your underlying dark matter distribution, you need a simulation, these hydrodynamical simulations. Now, these hydrodynamical simulations take about 2 to 3 weeks to run on high-performance computers. So I'm glad you're having fun going through my old videos. That is very nice to know. So this is a problem because these simulations take 2 to 3 weeks. Obviously, you can't do a simulation every time you want to change something about the universe. So this is the problem we want to solve. But now going back to the question here, why specifically hydrogen clouds? Is it simply because hydrogen is the most abundant? It is absolutely because hydrogen is the most abundant. So about 95% of the universe is hydrogen. A bit of it is helium, and then there's everything else. No, I think by now, 75% of the universe is hydrogen, like 25% is helium. The rest is just a very, very small percentage. So hydrogen is the easiest element to form, and it is the most abundant one in the universe. Basically, anytime you have cosmic dust, it's going to be mainly hydrogen with very, very small amounts of other parts as well. But the good thing about hydrogen is it triggers these specific absorption and emission lines, which we know exactly where they should happen. So this is what we call the Lyman-alpha transition, and the Lyman-alpha transition happens with hydrogen. Let me just go back to this image because it is a very nice question. So you see these bumps to the right that don't have any labels. So you have the first big peak, which is a hydrogen emission. And then if you go to the right, there's these other smaller peaks. These other smaller peaks are actually from other slightly heavier elements. I think one of them is a beryllium peak. Not beryllium. Beryllium is heavy. Hydrogen, helium, boron. Sorry, boron. The light one. And the other one might be from lithium, but I'm doing that by memory, so I don't remember exactly what they are. But you do have the heavier elements when you go to higher parts of the spectrum. But hydrogen is the one that's going to cause the emission lines that we want to absorb. I hope that answers your question. As always, if 90% by number and 75% by mass. Thank you, David. That is why I had both of those numbers in my mind. So hydrogen and helium are the most abundant elements in the universe. Exactly. So I hope that answered the question. If not, as always, ask follow-ups. So I mentioned here that we have the problem with Lyman-alpha data, that going from your model to the flux, which is what you actually observe, requires this simulation. Now, usually what we want to do in cosmology is you try 1,000 different versions of your model or 1,000,000 different versions of your model, and you compare them, each one to the data. I wondered if it also something has to do with the fact that the gap is 13.6 eV for hydrogen. Yeah, I believe that corresponds to the Lyman-alpha energy, so I'm going to say yes to that. But once we get to specific numbers, my brain always has issues. I know like 4 numbers in cosmology, and the rest are just like, I guess I don't need that number. Just set everything to 1 and we're all happy. So usually what you want to do is you want to test 1 billion different versions or 1,000,000 different versions of your model, where you change the different parameters very slightly. You change the amount of dark matter, or you change what dark matter does, or you change the temperature of the universe. And then you see which of all of your predictions best fits the data that we have. And to do this, we use a likelihood. Now, the problem with Lyman-alpha data is that you would need to do a hydrodynamical simulation for every one of these 1,000 or 1,000,000 tries. And if each simulation takes, so a hydrodynamical simulation basically means you take all of your knowledge of physics, you make particles in a box, you make a box and you say, here's 10,000 particles, you press the on switch and you see what happens. You see how matter evolves. And this simulation is how we deal with nonlinear physics. If it's linear, you solve an equation, it's easy. If it's nonlinear, you need the computer to do a simulation to predict what's going to happen. Now, obviously, if these simulations take 2 or 3 weeks, you can't wait 2 or 3 weeks every single time you change one of your underlying parameters, because at some point, you're going to run out of computing time. So this is the problem we set out to solve. In 2018, when we started on this, we asked the question of, can we develop a technique or a likelihood that allows us to do this without needing the simulations? So can we skip the whole step of the simulations? And how do we go about doing this? And this was the objective of this paper. And we didn't want to do it for one dark matter model. We wanted to do it in a way that it could be used for many dark matter models. So it doesn't just depend on, maybe I'm saying dark matter talks to baryons, maybe I'm saying dark matter is warm. We don't want it to depend on that. It should work for any of these dark matter models. Now, of course, this is a big task, trying to develop this likelihood. This is why it's taken us over 4 years. Now, the cool thing is, we've actually found a way to do it. I realized it looked like I was pausing for dramatic effect. I just remembered I needed to drink my tea. It was not intentionally for dramatic effect, but it felt cool. So, the approach we set out to do, based on some previous work by the Trieste group, was rather than focusing on each one of these simulations and the output, was to ask ourselves, what is the actual effect of these dark matter models? What are they actually doing to the universe? All of the models that we're interested in, what they do is they reduce the amount of structures you can form on small scales. If your dark matter is warm, which just means it's not as cold and moves a bit faster than we thought it was, it drags around the other species in the universe and it prevents galaxies from forming as efficiently. So on small scales, you don't get as many structures, you don't get as many things, which means you would have fewer hydrogen clouds. If you make your dark matter bump into photons or bump into protons or neutrinos, you overall reduce what everything else can do. The dark matter can't sit down and form galaxies efficiently, and so you reduce the amount of structures. So with this in mind, we're saying that all of the models we're interested in stop hydrogen clouds forming on small scales, or stop dark matter clustering or clumping together on small scales. So what we do now is we focus on this specific amount, the quantity, the amount by which we're reducing how structures can form. And obviously, we're always going to have to compare it to something. If we're saying we produce less structures, then what? And our comparison is always a standard model of cosmology, lambda CDM. So what we do, let me just go to a specific figure in the paper, actually, and then I will share a screen and share the paper. I've just lost the figure in my paper. You'd think by now I would know where everything is in my paper. Looked at it 100 times in the last week. Okay, so bringing this one up now. So this is the first figure from the paper. So it is like a grid search with edge cases or something like sensitivity analysis. Yes, I will get to that in 1 sec, but yes, that is where we're heading basically. So what you can see here is what we call the transfer function. Now the transfer function just measures how we're forming matter or how we're letting things clump together compared to our underlying lambda CDM. So if we're doing exactly the same as lambda CDM, exactly the same as our standard model of cosmology, we would expect a flat line at the number 1. A flat line at the number 1 because we're forming 100% of the structures that we form in lambda CDM. But if you change the way you form structures, instead of getting this flat slope, what you're going to get is one of the colored lines you see here. So we've just chosen 4 randomly chosen examples here. The purple one and the blue one are different models of dark matter talking to protons. The yellow one here is when you have dark matter that is not as cold as we expect, so it's moving slightly quicker. And the green one here is dark matter talking to dark radiation, which is just another type of dark matter that doesn't have mass. So all of these different things, you can see they affect the way we form structures in different ways. So in the models we've shown here, the one we list in purple as dark matter baryon model 1 really does suppress the formation of structures a bit to the left, while the other ones are a bit further to the right. Now, on the horizontal axis here, we have the overall size, same as before. So on the left, we have large scales. On the right, we have small scales. So the further to the right you go in this figure, the smaller the galaxies or hydrogen clouds that you're looking at are. So you can see here that overall, all of the models we're interested in have this effect where they reduce the amount of structures we can form. As always, if there are questions, please do feel free to ask. So we've reduced the amount of matter that can cluster together. So now we've broken the problem down into this one figure, this amount by which we're reducing matter. So what we did is, okay, we can't run a simulation for every possible deviation here, for every possible suppression to the left, to the right, up and down. But we can come up with one formula that describes this shape. One formula that is flexible enough that it can describe multiple shapes. And this is what we call a parameterization, because you're just coming up with a few parameters to describe how this happens. And we came up with one that has 4 parameters. Our 4 parameters are called alpha, beta, gamma, and delta. I think we're all becoming all too familiar with the Greek alphabet these days. So these are the 4 parameters we have: alpha, beta, gamma, delta. Alpha is going to tell us how far to the left or to the right on that figure we are. Beta and gamma are going to give us by how much we're suppressing, or this overall shape. And delta is going to tell us if we reach 100% suppression, if we reach 50% suppression, if we reach 20% suppression. Is there any type of dark matter that would increase the number of structures? So there are some models where you change the initial conditions of inflation, and that could actually increase the way dark matter forms in the universe. You basically make the dense regions of dark matter in the early universe denser than in our standard model. There are models that do that, but we did not look at any of them here because we were focusing on suppressions. About the process itself, how did you keep working on this paper for 4 years since it started in your PhD? Was it stressful to work on a project? Yeah. So this project started during my PhD. And for a time it was priority, and I wanted to include it in my PhD thesis. And in fact, if you look in my PhD thesis, which is publicly available, this paper was listed as in preparation back in 2019 when my PhD thesis was written. It was a ridiculous amount of work. We thought so many times that it might not finish. Fortunately, I didn't need this one to graduate because I had enough other things I could talk about in my thesis. But yeah, it's honestly, it's not been great for me to have this paper hanging over me for 4 years. And especially because I was always the one driving the project. After the first year, Neil Schoenberg joined as well, and then we were jointly driving the project. But because of all of the numerical setbacks for all of us, it became lower priority. So it was always a project we would come back to when we had time in between other projects. But I really wanted it done. And in the last 9 months, I've really been pushing on getting this paper done. So giving this paper time that I could be spending on my thesis or on other things was always an issue. And it was always the thing of how much time should I spend on this project? But then you get to the point of like, well, I've spent so many years on it, now I want it done. But yeah, about 9 months ago, I decided I just needed this done. And I've been pushing, me and Nils have been pushing on getting this done. Can you do that with the Planck data from the early universe? Nice. Are these Laplacian transfer functions or any other transform? Also nice question. On to Scott's question. So unfortunately, Planck data doesn't go down to these small structures. So Planck data is the data we have of one of my favorite things in the universe. And now that you said Planck, you know what has to happen. So Planck data is one of the coolest things we have. It is the latest measurement we have of the cosmic microwave background radiation, which is my favorite thing in the universe. And of course, that's image 1, and I was at image 27. So I'm getting back there gradually, and it should be this one here. CMB, cosmic microwave background radiation, the best thing in the universe, tells us everything we want to know. I did my whole stream 2 weeks ago about the CMB, so I'm not going to go into detail now. Now, the problem with Planck data is it focuses on a different different sizes. So the Planck data could tell you about things to the left of the figure I was showing, whereas we're now interested in going further and further to the right. So all of our analysis will include the Planck data, but we want to go beyond that. So these are not Laplacian transfer functions. These are we call it a transfer function because it's redshift independent, so it works at any point in the universe. So at any point in the history of the universe. So that's cool because by getting this difference today, you can then figure out how different they were in the early universe as well. But it is not related to a specific transform. We just call it a transfer function. Shri, I hope I always try to give honest answers, especially about the ups and downs of academia, because I think that's conversations we should have. And I will be the first to admit that this paper has been a big deal for me. It's also not been great for my mental health, but it's done. So that's good. So in our likelihood, what we've done is said, okay, you can't do a simulation for every possible combination here, but we have this parameterization alpha, beta, gamma, delta. And what we can do is we can choose good, well-motivated values of alpha, beta, gamma, delta. Is the Greek alphabet used as a chronological scale or specific to functional aspect? Yeah, honestly, the authors who first came up with the three parameter version, just went with alpha, beta, gamma because they needed 3 variables, and then we just followed on and added the delta into it. There's no deeper meaning to it. The best paper is a finished paper, absolutely. The best paper is a paper you are done with, especially after 4 years and 3 months. Not that I was counting. So what we decided to do is take these 4 parameters, choose well-motivated cases of alpha, beta, gamma, and delta. And for each one of these, which we call benchmark cases, we ran a simulation. So we ran 200 of these complicated 3-week-long simulations. And we use these simulations to build a grid of alphas, betas, gammas, deltas, the corresponding flux from Lyman-alpha, and the corresponding likelihood, or how likely this model is, given the actual Lyman-alpha data we have. There's also a lot more going into it than these parameters, because you have things like the temperature of the intergalactic medium, and you have the ionization, and you have a bunch of things. But basically, we ran 200 simulations with very different variations of all of the parameters, and we use this to build a grid. And this grid is the basis of our likelihood. I meant compose an equation that, just missed a few questions there. Let me go back. I meant compose an equation that satisfies all the points on the data curve. I thought the error bars were no longer able to be reconciled. I'm not really sure I get what you mean here with the question, Scott. If you want to rephrase that, maybe I'm not completely sure what you're referring to here with the Planck data and finding the equation. So what was your first question again about Planck? Can you do that with the Planck data? Right. So I think you mean finding a parameterization to describe the Planck data. For that, we have lambda CDM. Lambda CDM is the best model we have to describe the Planck data and a bunch of other data sets. I hope that's close. Your simulation had, in essence, 4 inputs. How many output values for each set of the 4 inputs? So our simulations had a lot more than 4 inputs. They had the 4 parameters, plus a lot of astrophysical parameters, plus some parameters related to the hydrogen clouds. And what it outputs is the flux. So we do our simulation, and what it outputs is the flux, which I'm going to bring up on screen as soon as I get back to the right slide. I know I could just share the slides quickly, and then you would see me going quickly through all of the slides, but that's not the point of this. So back to this here. This is the flux. So we input our alpha, beta, gamma, delta, plus the nuisance parameters, plus everything else, and what the simulation is going to spit out is this curve here. You can see here in green is what you get for lambda CDM, in red is what you get for a different model. So for each one of our alpha, beta, gamma, delta combinations, which are all listed in the paper, by the way, we have a table with all 200 values of alpha, beta, gamma, delta. What we get out is one of these curves here, and then we compare these curves to the data points. So what we have done is we have constructed this likelihood, which takes your model. So you can now come with any dark matter model that can be described by alpha, beta, gamma, delta. Or if the effects of your model, of your dark matter model, on how structures form can be described by alpha, beta, gamma, delta, rather than doing a hydrodynamical simulation that takes 2 or 3 weeks, our likelihood will take your model, it will interpolate within the grid, and it will find the corresponding likelihood of the data, of the model given the data. It's pretty cool. I'm breaking it down here into like we just do this grid. This grid has taken us 4 years to build. And it has a precision now which is of the order of a few percent. We have built a bunch of checks into the likelihood. So for an example, if the model you're trying to describe doesn't have any of our grid points close by, the likelihood will warn you like, hey, you're a bit far away from what we're doing. If you go beyond the region where we trust the grid, it will warn you like, hey, I wasn't built to do this. But in general, so at the beginning, we were using well-motivated grid points. And at the end, we were adding grid points that were necessary so that we would pass all of these checks. So that when you come with technically any model that can be described by this, you will be able to interpolate in the grid. The grid will be able to give you an answer. Let me just go back here. I remember you talking about two competing data sets that don't mesh the further back you go. Yeah, that's the Hubble tension, Scott. Unrelated to today's discussion, but also cool, and something we can go back to another day, perhaps. If you use neural networks as a replacement to the transfer function, people have tried. What some people are doing now is building a similar approach based on Gaussian processes or based on different emulators. They're not as flexible and they don't have as much precision as we've been able to get with this method. To rely on it, presumably you need to know how it behaves between the grid points. So we assume that there are no discontinuities. We assume that, if you can predict it in several places, we have no reason to believe that it's randomly going to be different in between. And we can run dedicated simulations for specific cases. You can choose random models and say, okay, here's what the likelihood predicts, this thing that we've built, which we call Lyman-alpha beta gamma delta, because we're so good with names. Should actually be Lyman-alpha alpha beta gamma delta, but we skipped the second alpha, and it's Lyman-alpha beta gamma delta. And we can actually run a dedicated simulation and compare it to the output of our likelihood. And in every test we've tried, the likelihood is correct. So you can choose random points and do the test. You can do the simulation. So there is a way of doing the cross-check. And we have done this for a few models. And it works for all the ones we've tested. So with this likelihood, we claim, and it's a big claim, that you can test a lot of different dark matter models. If I understand it correctly, you have built a way for us to compare different models of dark matter, their viability, and how likely one is over the other based on everything we know about power spectrum. Not everything we know about power spectrum, because it relies only on Lyman-alpha data, so there's no BAO data here. There's nothing to small scales, but you can include that as an extra. But this likelihood is based on everything that Lyman-alpha data, specifically Mike and high-res experiments, can tell us about the power spectrum. So yes, that is a good summary of what we've tried to do here. It's a huge amount of work. It's taken 4.5 years for a reason. And honestly, I am super proud of this paper. I am really happy with the paper that we put out. I'm honestly, really happy with it. There's some of the papers that you finished thinking, yeah, that was okay. It was a good paper. But this one, I am honestly so proud of this paper. So once we built this likelihood and claimed that we can do a lot of stuff with it, we had to test it. So we found 4 different dark matter models to test it on. The first one is the case where you have warm plus cold dark matter. So some cold dark matter and some warm dark matter. The second and third model we tested on is dark matter bumping into protons, so baryons, with different energies. So whether it's more dominant in the early universe or slightly later on. And the fourth case we tested, is when you have dark matter bumping into dark radiation, which is a type of massless dark matter. So I'm going to show you the figures, and I'm going to start with the first one. Just scrolling in the paper here. So what I'm going to show you now is how we present results often in cosmology. If I were Greek in origin, I would be intimidated by how rife and pervasive Greek letters have made it into mathematics and physics. Yeah, and apparently I have been told by many Greek people that non-Greek people mispronounce a lot of the letters, and apparently it's very frustrating because we use them so much in physics and mathematics, and almost everyone who is not Greek mispronounces them, and apparently it's a bit frustrating, and I can really see why it would be. Okay, so what you see here is figure 2 from the paper. We were at figure 1 before. We're not going to go through all of them because I'm already 55 minutes in. Wow, time is flying here. So what you can see here are 2 triangle plots. You have the big one on the left and the slightly smaller one on the right. So what a triangle plot does is it shows you, if you break it down to 2 of the parameters of your model, how likely are this combination of parameters given everything you know. So the colored region is allowed, the white region is not allowed. So for an example, if I focus down here on this one, what I'm showing you here is 2 simple parameters, h0, which is the expansion rate of the universe, and sigma h, which tells us how structures are being made in the universe at specific sizes. And what you can see here is we have this very nice oblong. Now this oblong, if you notice on the vertical axis, it says S8, on the horizontal one it says H0, and you can see we have this oblong. So this oblong is the allowed region. Anything in the white region is not allowed. Anything in the light blue region is allowed at 1 sigma. Sorry, allowed at 2 sigma, and anything in the smaller region is allowed at 1 sigma. This means that we are 95% sure that the combination of these 2 parameters lies in the big oblong, and we are 68% sure that it lies in the smaller oblong. Keep asking questions, let's get this to 2 hours. I can't go for 2 hours today because I do have something very important to do in about an hour from now, an hour and 20 minutes. So I can't go for 2 hours today, but we will go past the 1 hour mark because I'm not done yet. Okay, so this triangle plot tells us after running all of our models, all possible values of sigma 8 and h0, we know that the actual answer according to this data needs to lie in this shape here. Then what you can see where we have these kind of mountain ones is just a one-dimensional projection of this oblong. 0 was split into 2 letters. Yes, Omicron and Omega. Omicron and Omega. Yes, small and big O's. Yes, I think we're all familiar with at least one of those now. But this is actually the one I want to show, the figure on the left. So we're going to focus on this very, very messy splodge in the kind of middle of your screen currently, where on the vertical axis, we have FWDM, which means the fraction of warm dark matter. And on the horizontal axis, we have the mass of warm dark matter. So here what we're looking at is how massive the dark matter is allowed to be, and how. So if we have a cold dark matter and warm dark matter, the fraction is what fraction of dark matter is warm, and the mass basically tells us how warm it is. Now let's go back to the questions. You're going to present this paper in your journal club on Wednesday. Oh, awesome. Thank you. So thank you for joining the stream, and thank you for choosing my paper for your journal club. That's really cool. If you have any questions, you can feel free to email me at any time if you don't find your answer here or in the paper. How do these regions of allowed likely parameter ranges compare with already known constraints on dark matter? Excellent question, Paul. So let me focus on this middle figure here. Now, what you can see in yellow is the data we obtain from Planck. Let me just check that that is indeed correct. Yes, yellow is Planck. And you can see here that Planck plus BAO, we include BAO, basically Planck data, allows for the whole region. Planck data here does not provide any constraints. The Lyman-alpha constraints you can see in blue. And if you focus on the green one is what I told you before of our coverage test. The green one tells us where our grid can be trusted, which points can our grid actually do. And you'll see that the green one fills the entire box, which means every possible point that we have looked at passed all the checks in our likelihood. Now, the blue one here gives you the constraints. This is very cool because you see we have this red line that just draws the side of the blue region. This is the constraint we get on the combination of the amount of dark matter that can be warm and how warm this dark matter can be. This here is an extremely useful cross-check because this is a model that people have studied in the literature. This is something that has been done before. And with our new method, we were able to reproduce what other people have done. So the way they did it before is running a simulation for each one of these underlying cases. we were able to get the same constraints as other people in the literature, which means our likelihood appears to be doing what we built it to do. So for the case of some of the dark matter being warm and some of it being cold, our likelihood did exactly what it should do. It gave us the number that we know it should have given because we had this number already in the literature. So this is a good check that our method is working. This is cool. But now I want to talk about the second case. Now, the second case we looked at is the idea that dark matter could have bumped into protons, which are normal matter, very, very, very lightly in the early universe. And this is not just gravitational. What we're saying here is there is a tiny, tiny bumping, like they actually get close enough where they can really exchange something or have some type of interaction. So there really is something going on between the dark matter and the proton. So we're asking the question here of, can you have any type of interaction between dark matter and protons in the early universe? The more interaction you have, the more you're going to produce the hydrogen clouds. So the more Lyman-alpha data is going to say, okay, I've looked at these hydrogen clouds, maybe don't do that. So now with our new likelihood, we wanted to test the case of dark matter doing this. And this has been done before. What hasn't been done is asking the question of what if only part of the dark matter does this and not all of it? So instead of saying all of the dark matter can bump into these protons, what if only 10% of the dark matter can, or 50%, or 1%? So we allowed this number to be one that goes into our analysis. So we can test it for any fraction and for any interaction rate. So we have how much dark matter is interacting and how much of the dark matter is interacting. And this analysis with Lyman-alpha data, we believe we are the first people to do. And I'm going to show you the results because the results are very, very nice, at least in my personal opinion, which is what matters because I'm the author on the paper. And I get to do that this time. Okay, so what I'm showing you here are the results of the dark matter bumping into protons case. Now we're focusing on the triangle plus on the left where we have these 6 different panels. You see there's a 3 with the kind of mountains and all the messy ones in the middle. And I want to focus on the one that has the most stuff in it, which is kind of the second row, first column. Now here we're looking at the allowed region. On the vertical axis, we have the fraction. So the further down you go to the bottom of the screen, the less amount of dark matter is allowed to bump into protons. And on the horizontal axis, we have how much the dark matter and the protons might have interacted. The further to the right you go, the stronger the interactions. The further to the left, the weaker the interactions. Okay, now first of all, in yellow, we have the Planck constraints. The Planck constraints, we have put a line on the side so you can see where the Planck data constraints is. This is the black line. Everything to the left of the black line is allowed by Planck data. Everything to the right of the black line is disfavored by Planck data. So already Planck tells you that is not possible. The green one, again, which is perfectly overlapping with the yellow, which is why you might not see the yellow. The green one shows us if we could apply our method in this case. And you can see that the green covers everything within the Planck range, which means that everything that could be covered was covered by our likelihood. And then in blue and purple, but they're perfectly overlapping because it's just 2 different methods we have within the likelihood. It's not important, but we put 2 different ways of doing this interpolation in the grid, and they both produce the same results, which is also very nice. But the blue contour here, the blue colored in region, is what we actually get from Lyman-alpha data for the fraction of dark matter that can interact and how much it can interact. We border this with the red line. So basically what the Lyman-alpha data does is it cuts out the region in between the red and the black lines. So all of the stuff that is colored in dark blue is stuff that we can do, that dark matter is allowed to do. Lyman-alpha data can't tell us anything about that. Everything in the white region does not work. And everything that is in between the black line and the red line is excluded based on our new likelihood. So our new likelihood tells us all of this region in between the red and the black line is not possible. So this is cool because this is new. This is something that we think we are the first to really show this type of figure. But there is something else very, very interesting here. Now, you'll notice that when I showed it before, In fact, let me just go back to do the comparison. When I show this one here, you'll notice that there's all of it has the same amount of kind of dark blue. There's not a region where the dark blue clusters or where there's more dark blue and less dark blue. It's kind of everywhere. But if we go to this one here, you'll notice that the left part is very light blue, while the right part is darker blue. This is telling us that the part on the right here, still to the left of the black line, but not completely on the left of our panel, is appearing more often in our likelihood. So our likelihood likes these points more than ones on the left. What this is telling us is that the data prefers this region. So the data is slightly shifting to this darker blue region. This is what you can also see in the mountain up above. Now you see the yellow one on the left-hand side is flat because all parts on the left are equally valid, and then it drops off. The green one, which is our check, does very similar. But then the blue and the purple one start off low, then they peak, then it goes down again. Now it goes down on the right because we know the data can go further there. Now the question is, why does it go down slightly on the left? Because what this is telling us is that the likelihood prefers this slightly darker blue region over the region on the left of it. But if you remember, I said on the horizontal axis, we have how much can dark matter interact. The further left you go, the less interactions you have. So what this is showing us is that the Lyman-alpha data is actually saying that slightly more interactions than zero is better than fewer interactions. So it seems to say that the data prefers dark matter to bump into protons and dark matter not bumping into protons. Is it strange that the higher likelihood regions are close to the white zero regions? That is a very good question. And of course, it would be nice to allow this to go further to the right. But if you look especially at the bottom, you can see it doesn't completely go all the way. So if it went all the way to where the black line is, then it would be a reason of concern. But you notice it doesn't actually touch the black line. So there's a bit to the right of the dark blue and a bit to the left of the dark blue. It's like there really is a region where it's happier. What does this mean? This means that Lyman-alpha data, with our analysis, is showing that maybe these interactions are actually better for the data than no interactions. And I want to be very clear here. This is what we call 2.5 sigma significance, about 2 sigma significance closer. It's not a big amount, it's not overly significant, but it is a hint that the likelihood is preferring dark matter to talk to protons than for it to not do this. Now, again, our standard model of cosmology assumes that these interactions do not happen. So what we're really saying here is that the Lyman-alpha data seems to prefer something that is not our standard cold dark matter. And the word prefer is a very big word to use here. I don't want to say that we found a preference for dark matter interacting, but rather there is a hint here. There are hints that moving away slightly from the standard cold dark matter paradigm actually seems to be agreeable with the Lyman-alpha data. And some of you who have been here for a while, thanks for stopping by a bit. It's really great to see you. It's really great to have you here. So those of you who were back on my streams back in November might remember me having a similar discussion when I had my co-author on, where we found something similar for dark matter bumping into neutrinos. I will link to the video as well. Now this is really cool because we put out a paper late last year, where we showed that there was a mild preference for dark matter bumping into neutrinos. This was using Lyman-alpha data and the old version of this likelihood, because we put out an intermediate version of this likelihood called alpha beta gamma. Using alpha beta gamma, we found a slight preference for dark matter bumping into neutrinos. And now with a much more advanced version of the likelihood that has undergone a lot more tests and has a lot more precision, we are finding a slight preference for dark matter bumping into protons. Now, this is really cool. And what this is telling us is that it might not be dark matter bumping into neutrinos. It might not be dark matter bumping into protons. But the Lyman-alpha data does seem to like something that is not standard cold dark matter. And I'm just going to show you one more figure from my paper to really make this point. This is going back to the Lyman-alpha flux, which is the thing I've showed a few times already. Now, what you can see here is the flux of different models. So again, high-res data is shown with crosses, mic data is shown with circles. These are the data sets we are using. You have the 4 different redshift bins. So you have high redshift, low redshift. You have the flux on the vertical axis and the scales or the size on the horizontal axis. Okay, in purple here, let me just zoom in very slightly here because I want you to see this properly. So in purple here, we're showing lambda CDM, so what our standard model predicts. In green and yellow, we're showing the 2 different methods for dark matter bumping into baryons that we developed here. And in blue, I'm showing the case of the dark matter neutrinos from our other previous paper. And if you compare the blue to the purple, you can see that the blue, especially in the redshift bin of 4.6, so the second from bottom line, the purple one doesn't go through the data points as well as the blue one. Thank you for stopping by, David Dunn. It's been great to have you here. So, yeah, what you can see here is both the dark matter bumping into neutrinos and the dark matter bumping into baryons slightly shift this flux in a way that the data is happy with. So both of these behave very, very similar. So basically what we're saying here is that any model that can do this, that can change the flux, Lyman-alpha data is slightly happier with than lambda CDM, than our standard model of cosmology. You're waiting for the breathless clickbait headlines, Cosmology team led by Diana Hooper breaks physics as we know it. You know, honestly, I might do a press release for this paper. I might contact people to do a press release, but we are not going to do clickbaity titles, not on my paper. Now, I want to be very careful here because we are not saying we have found proof that dark matter bumps into something. We're very careful not to say that. We have found hints that with this method we have developed and with this data, there seems to be something odd, something that the likelihood prefers or the data prefers that is not lambda CDM. Now, there could be other reasons for this. Now, at this point, it doesn't seem to be something specific to our method because we found it in the intermediate one, we found it in the final one. And for these dark matter baryon models, we ran the specific simulation. And the full simulation gives us exactly the same result as our likelihood. So the likelihood is giving us what we would expect it to give us. We have ran these tests. We have a whole appendix discussing these tests. But it seems to be that what we found is correct, or at least it's not caused by the likelihood. It doesn't mean it's correct, but it's not caused by the likelihood. Now, there could be something else causing it. And again, it's a very mild preference, but it is a hint of for non-standard dark matter. And this is very, very, very cool. And I also just want to add a personal story here of how crazy I was going when we were doing these papers, because I was working simultaneously on both of these papers, the neutrino one and this one. And we had this mild preference in the neutrino paper. Me and my co-author for that paper, Matteo Luca, were going crazy every day. Like, is this real? Is it not? We were running hundreds of tests. And every day we would wake up like, no, it's not real. And the next day we'd wake up like, yes, it's real. You know, we did so many tests. And then in parallel, I was working on this other paper, the dark matter baryon ones. Once we finally got the likelihood working and I did my simulations and I looked at the results and we'd found the same thing. And at that point, I was just like, oh my God, it's 2 separate papers. We're finding this in both cases. This is not a coincidence. Honestly, I was going so crazy with this. And the moment we got it in the second paper as well, was like, okay, I guess we're actually going ahead with this. It was a roller coaster. Both of these papers have been roller coasters of emotions. So it's pretty cool. It's pretty cool. If our solar system was in the center of a void, would any of our research into this and other early universe study be different or easier? There are people looking into that, into how a local void would impact our results. And it does affect a few things, but we have not found clear evidence that we are in a void. So we don't think that's the case, but it would affect a few things. I'm not sure if it will make it easier or harder, it would just make it different. But yeah. So then there was another question by Anne just now of what's the next step in the process after these 2 papers? And I really like that question because There's quite a few things to be done now. On the one hand, we have just made this likelihood that we claim can be used for many dark matter models. We tested it for 4. I've shown you the results here of 2, but there are 2 other cases I don't have time to discuss. And the likelihood also appears to do well, but it doesn't find the preference or this potential deviation except for the dark matter baryon case. So the next step for me personally is to clean the likelihood and make it publicly available, because this is not just a tool we've developed for us, this is a tool we've developed hoping that people are going to use it. There's a few coding things we need to clean up, some debugging statements that need to be cleaned, but when the paper is accepted and published in a journal, the likelihood will be made publicly available for anyone to use. It's going to be out there in the world. So the next step for me personally is to fix that, get that ready to go out public as well, the actual code behind the project. The next steps are to find what other models could do this, because we know that now there are at least 2. There's the dark matter neutrinos and the dark matter baryons. One step is to find out what other models could do this and what do these models have in common. So why these models and not other ones? And why has this not been found before? The next thing to figure out is what happens if we add different Lyman-alpha data. Because here I use data from Mike and Hyres, and there are more precise data out there coming from XQ100. Now, XQ100 is a different Lyman-alpha experiment. The reason Lyman-alpha XQ100 data was not included here, it's fun, it's actually because XQ100 increases the precision of Mike and Hyres by a huge amount. We know that our likelihood has some uncertainty, some error associated to how we do this interpolation. And it's fine for Mike and Hyres because the error we make in our method is always smaller than the error in the actual data. However, for XQ100, the data is so precise that our method would add too much uncertainty on top of it. So we now need to figure out how we can make our method better so that we can include the next data set to actually see what the next data set tells us. And there's a bunch of other projects that can be done with this, but those are the next steps for me. So just want to do a big recap here. We put out a new paper this week that has been ongoing for 4 years and 3 months, not that anybody was counting. Now, in this paper, we have developed a new way of using Lyman-alpha data to study dark matter models. We think it can be applied to multiple dark matter models. We tested it on 4 cases. For dark matter that is slightly worn, we were able to reproduce results that other people had done, which served as a good proof of principle. And we were able to really... There was also a fun discussion about how you do this analysis, where we find just some statistical discussion that I actually think is a really nice detail in the paper, but I'm not going to go into because it's just a random statistics conversation, but I like it. For dark matter baryons, in one case, we found a mild preference over lambda CDM. In the other case, we've updated results. And in the case of dark matter bumping into dark radiation, which is just massless dark matter, we actually found that we couldn't put results because all of the data is already constrained by Planck, and Lyman-alpha data doesn't improve on this beyond what Planck does. So that was interesting to know, and we know physically why. And it was also to show that even in this limiting case, the likelihood did what we expected it to do. So yeah, this paper has mainly been about developing this new technique. Is there any possibility to get funding grants to supervise grad students to do these follow-on studies? Interesting that you asked that, Paul. Yes and no. Grants are always difficult to get. Funding is always difficult to get. But it is definitely something one could do. And I am purposefully being vague about that answer. It is a very timely question. So yeah, it's very interesting in my opinion. This has been a ridiculous amount of work. It's probably the paper I've invested the most time, energy, and numerical effort into, and simulations. It's been a huge amount of work, but I'm honestly really happy with what we did. And I really hope that the community likes the paper as well. I hope we get good feedback. And I do hope that our likelihood will help us understand dark matter, or help us use Lyman-alpha data. So it's exciting, and it won't be a couple months. We'll put the likelihood out publicly, and then it's ready for anyone to use. And it will be very interesting to take our studies further and see what exactly is going on with dark matter bumping into stuff that seems to be something Lyman-alpha data likes. It's fun. And I'm so happy to have this paper done. On a personal note, it's just getting this paper out. I'm so happy. It's done, it's out there, it's been so much work, but yeah, must be nice seeing your hard work pay off. Honestly, yes, this is the paper that I am happiest to have out, because of how much work it has been, how much mental energy has gone into this. Are you in the process of other papers now, or on a break now? There's no rest for the wicked, right? That's how it goes. I am usually always in the process of other papers. Currently, I am actually on a break, though. As of Friday afternoon, we put this paper online on Thursday. It appeared Friday morning, and Friday afternoon is like, I am done. I am actually on a break now. I have all of next week off, and the following Monday off. I'm taking a small holiday, and the plan is to completely not think about work for 8 days. That's not going to work because I'm very bad at doing that, but I am going to be on a break for the next 8 days, and then I will come back recharged, revitalized, and ready for the next paper. I do have too many projects to count. I realized today I should not count how many projects I have, because it was pointed out to me that actually I have too many projects, and that might be true. But in any case, I have a lot of other ongoing work as well that I'm also very excited about. And yeah, I am in the process. I'm not actually at the writing stage with any of the other papers, so now there will probably be a gap before my next paper. But there are always ongoing projects. But I am actually on a slight break now for the next week, which will be very good for me. On the topic of being on a break, next Sunday, I think I will do a live stream. I'm not 100% sure yet, because I will technically be on a break, so maybe I skip it. But next Sunday is Pride Day, and I do want to do kind of a queer space theme, but I haven't yet figured out the details. So next week there will either be no stream, or there will be a Pride special, one of those two. Haven't yet figured out which of those two. It will very much depend on things that happen the next few days. But if there's going to be a stream next week, I will advertise it on the Friday or the Saturday as usual. It's announced on Twitter, and I create the live streams at least 24 hours in advance on YouTube. So I will advertise if I do something. I still need to decide if I will do something. That will come soon. I need to think over the next few days and decide. But if I do something, it will be a Pride special. There's a couple of people who might have already semi-volunteered who I'm going to try to convince to join me. We'll see. So no guarantees yet, but in any case, the week after I'll be back to regular schedule, broadcasting on Sundays. So Sunday the 3rd, I will definitely be around. Sunday the 3rd, yes, I will definitely be around. But next week, I'm not sure. We'll see. We'll see how the wind is blowing at the time, and how the stars are aligned and things. That's so nicely. Okay, so thank you everyone for joining. This has been great fun. I hope you didn't have too many lingering questions. If so, as always, leave questions. You can leave questions on the YouTube video afterwards, and I will try to answer them. I hope you enjoyed hearing about my new paper. I was very happy to talk about it. Very happy to be done with this paper. And we did have some really cool questions, so thank you for that. As always, if you're new here, or even if you're not new, make sure you're subscribed to the channel, like the video, leave a comment down below, do all of the usual YouTube stuff to boost my channel. I do appreciate all of you who click the like button and do those things, so thank you for that. And to all the fathers out there, happy Father's Day in several countries of the world. So congrats again. Thank you, Scott. Thank you, Ange, for the nice messages. Will Google Lyman, who was this guy? Yes, Lyman was a very interesting person, actually. I believe he went to Harvard. There's a plaque for him. Is it at Harvard? I think there's a plaque. I know I saw a plaque for him, but I visited like 9 universities in the span of 3 weeks. So might have been Harvard, might not have been. Okay, anyway, thank you everyone for joining. This has been great fun. I hope to see you for the next live stream, either in 1 week or in 2 weeks. We'll see how things go. And in the meantime, I hope everybody stay safe. I hope you all stay safe and